given that we know how the x operator is defined, we can also think easily about what is the expectation value of x on a wave function, something that you really know, but now maybe becomes a little clearer. Here you're supposed to do psi star of x times the x operator acting on psi of x. But we have the definition of this, so this is, as you imagine, dx. I should put primes maybe. Well, I don't have to put primes. dx psi star of x, x psi of x, which is what you would have done anyway. Well, given that we've started with this, we can ask also if there are eigenstates of the x operator. Yes, there are, but unfortunately they are a bit singular. So what should be an eigenstate of x? It's some sort of state intuitively that has a definite value of the position. So it just exists for some value of x. So it's naturally thought as a delta function. So let me define a function psi sub x0 of x. So it's a function of x labeled by x0 and define it to be delta of x minus x0. So I claim that is an eigenstate of x hat on psi x0 of x is equal by definition to x times psi x0 of x, which is x times delta of x minus x0. And when you multiply a function of x times a delta function in x, it is possible to evaluate the function that is being multiplied by the delta function at the place where the delta function fires. It has the same effect on integrals or anything that you would do. So here, this is equal to x0 times delta x minus x0. You evaluate the x at x0. And finally, this is x0 times that function psi x0 of x. And therefore, you've shown that this operator acting on this function reproduces the function. That's the definition of an eigenstate of an operator. And the eigenvalue is the number that appears here, and it's x0. So this function is an eigenstate of x hat with eigenvalue EV x0. The only complication with this eigenfunction is that it's not normalizable. So it doesn't represent a particle. It can use to represent a particle, but can be used to represent a particle. But it's a useful function. You can think of it as something that can help you do physics, and don't insist that it represents a particle. So this is the story for position, and the position gets actually more interesting as soon as you introduce the dual quantity momentum. So what is momentum here? So momentum is an operator, and this operator must be defined. Now, you had a shorthand for it in 804, which is p hat equal h bar over I ddx. And this shorthand means actually that in what we call the position representation, where we're using wave functions that depend on x, well, the momentum is given by this operator. And the story of why this was the case was sort of something that was elaborated in 804, the work of de Broglie, that saw that waves the wavelength of a wave has to do with the momentum of a wave, and finally people understood that this would measure the momentum of the wave. So this is the operator, and therefore in the representation that we're working, representation is a word that has a lot of precise meaning, but now I'm just using it in the sense that, well, we're working either with x's or with p's. And we're working with x's. That's why p looks like something to do with x. So what is p hat on a wave function? Well, that's what this means. It's another wave function obtained by taking the x derivative. So that's the definition of it acting on a wave function. The one thing that must be verified, of course, is that this definition is consistent or implies this commutation relation. So you've defined it as an operator. X, we've defined it as an operator, but most of us think it doesn't look like an operator, it's multiplying. But it is an operator. So this one does look like an operator. It's a differential operator. And you can try to see if this equation is true. And the way to test these commutators is something that, again, I don't think is unfamiliar to you, but let's go through it, is that you test whether you try to evaluate this product of operators acting on a wave function. And if things work out well, we'll see, you should get IH bar times that wave function. If that is the case, you say, OK, I've proven that equation because it's an operator equation. The left-hand side of that equation is the product in different orders of two operators, therefore it's an operator. The right-hand side is another operator. It's the operator multiplied by IH, anything that you get. Well, if this is an operator identity, the operator on the left must be equal to the operator on the right, which just means that acting on anything, they must give the same answer. So if I manage to prove that this is equal to this, I've proven that for anything, that is the answer. Therefore, I can write the top one. And let me just do it, even though this may be kind of familiar to many of you. It's good to do this slowly once in your life. So let's go through this. So this says x operator, p operator on psi, minus p operator of x operator on psi. When you have several operators like a, b, c acting on psi, this really means let c act on psi, and then let b act on c psi, and then let a act on that. The operators act one by one. The closest one acts first. So here, I'm supposed to let p act on psi, but that means that thing. So now x is acting on h over I d psi dx. On this one, I have p acting on x psi, because that's what x hat psi is. Here, this is multiplication by x of a function of x. So this is just h over I x d psi dx. And here I have h over I d dx of this whole thing, x psi. And you can see that when you act here, you act first on the x, and you get something. And then you act on the psi, and you get this same term. So the only contribution here is equal to minus h over I, the d dx on x, times psi which is I h bar psi, which is what I wanted to show. So this is true, and therefore you could say that this definition is consistent with your definition of x, and they represent this operator.